Nearly half a century ago, humanity launched two spacecraft on a journey unlike anything ever attempted before. Their mission was as ambitious as it was extraordinary: to explore the unknown frontiers of our solar system and help answer some of the biggest questions about our place in the cosmos. What followed became one of the greatest scientific adventures in history. The Voyager 1 and Voyager 2 probes not only delivered the first detailed views of the distant outer planets, but they also transformed our understanding of the solar system forever. Decades after their launch, they continue to transmit valuable scientific data from interstellar space, now traveling more than 24 billion kilometers from Earth. But Voyager is far more than a collection of instruments and electronic components. It represents humanity at its most curious, daring, ambitious, and resilient. These spacecraft did more than capture breathtaking images of giant planets and their moons. They inspired generations, expanding our sense of wonder about the universe. To this day, Voyager 1 and Voyager 2 remain the most distant human-made objects ever created. As true pioneers, they ventured farther than any spacecraft before them, reaching regions of space beyond the influence of our world. Along the way, they revealed landscapes, phenomena, and celestial wonders that no human had ever seen in such detail, and in many cases, have not seen again since. When I look back, I realize how little we actually knew about the solar system before Voyager, recalled Voyager project scientist Edward Stone. Again and again, we discovered things we never even knew existed. So, what exactly did these legendary spacecraft uncover? What secrets did they reveal about the planets, moons, and the vast darkness beyond our solar system? For this special supercut, we're diving into the incredible story of the Voyager missions, from the creation and launch of the spacecraft, to their historic grand tour of the outer planets, and the extraordinary journey they continue through interstellar space today, all the way to the distant future that ultimately awaits them. It's one of life's great ironies that some of the most important advances in our understanding of the outer reaches of the solar system have come not from cutting-edge technology, but from aging machines. The Voyager probes carry onboard computers with less memory than the one inside a modern car key fob. Even today, they still rely on 1970s-era 8-track magnetic tape technology, making them older than many of the people watching this. This is the paradox of deep space exploration. The immense distances involved and the extraordinary travel times mean that spacecraft often become technologically outdated long before they reach their most ambitious destinations. Of course, Voyager 1 and Voyager 2 were never originally intended to travel into interstellar space. They were designed for a 5-year mission to explore Jupiter, Saturn, and their largest moons, a journey made possible by a rare planetary alignment that occurs only once every 176 years. After successfully completing their primary objectives at Jupiter and Saturn, however, the mission team expanded Voyager 2's itinerary to include flybys of Uranus and Neptune. Once those objectives were also achieved, NASA launched the even more ambitious Voyager interstellar mission. Its goal was to explore the outer boundaries of the Sun's influence and venture beyond them. This final chapter would take both spacecraft into previously unexplored regions of the solar system, including the termination shock and the hotter, denser Helios sheath, before eventually crossing the heliopause and entering interstellar space. But how did these remarkable machines accomplish so much beyond the scope of their original mission? The answer lies in a combination of durable technology and extraordinary engineering foresight. NASA's designers made a series of forward-thinking decisions that allowed the probes to vastly exceed their intended lifespans. Put simply, they were built differently. One of the most important decisions involved their power source. Each Voyager probe is equipped with a radioisotope thermoelectric generator, or RTG, which converts heat produced by the natural decay of plutonium-238 into electricity. At launch, These generators produced approximately 157 watts of electrical power, enough to run a laptop and perhaps charge a mobile phone. That may not sound impressive today, but it was more than sufficient for the spacecraft's needs. Although the RTGs steadily lose power over time, decreasing by half roughly every 87.7 years, they were designed to provide enough electricity to keep the probe's essential systems operating well into the 21st century. This long-term power capability was no accident. When the Voyagers launched in 1977, NASA faced a unique opportunity. The outer planets were approaching a once-in-176 years alignment, a configuration that had last occurred during Napoleon's era. This rare arrangement not only allowed the spacecraft to visit Uranus and Neptune with minimal course corrections, but also enabled them to use gravity assists from each of the giant planets they encountered. These gravitational slingshots dramatically increased their speed beyond what their own propulsion systems could achieve. While gravity assist maneuvers had been tested previously on NASA's Pioneer missions, the concept was still relatively new. The alignment also imposed a strict deadline. There wasn't enough time to plan additional follow-up missions, and Congress was unwilling to provide funding for the far more ambitious Grand Tour mission NASA had originally envisioned. Faced with these limitations, Voyager's engineers optimized the spacecraft for the possibility of a much longer journey and hoped future funding would allow the mission to continue. Each Voyager spacecraft carries 11 scientific instruments, many of which include redundant systems that can be switched on or off to conserve power and compensate for failures. For navigation and attitude control, the probes are equipped with gyroscopes, reference instruments, and 16 hydrazine thrusters, including 8 backups. Redundancy proved to be one of the keys to Voyager's extraordinary longevity. It became especially important when Voyager 2's primary thrusters stopped functioning after 37 years in service. Engineers were forced to activate backup thrusters that had remained dormant for nearly 4 decades. Remarkably, they worked flawlessly, demonstrating the exceptional quality of their design and construction. The spacecraft also carry custom-built onboard computers that, while primitive by modern standards, represented cutting-edge technology in 1977. Their camera systems are controlled by a computer command subsystem that manages fixed programs, including fault detection and correction routines. Another critical system is the attitude and articulation control subsystem. Despite its intimidating name, its job is straightforward: maintaining the spacecraft's orientation in space. The term attitude refers to the probe's alignment relative to Earth. Without precise orientation, Voyager's high-gain antenna would be unable to send or receive signals from NASA's deep space network. This capability is essential because the probes transmit with only about as much power as a household refrigerator light bulb. Across billions of kilometers, those signals become faint whispers, barely distinguishable from background noise. To maintain communication, Voyager's antennas must remain accurately pointed toward Earth, while NASA must know their precise locations. Otherwise, finding them would be like searching for a needle in a 287 billion kilometer haystack. Each spacecraft is equipped with a 3.7-meter high-gain antenna and an 8-track digital tape recorder capable of storing 536 megabits of data, enough for approximately 100 photographs. Although this represented a significant improvement over the earlier Pioneer probes, which lacked onboard storage entirely, it remains tiny compared with the capabilities of even the most basic modern smartphones. Despite these limitations, the tape recorders were built to extraordinary standards. Their manufacturer, Odetics, claimed they could process more than 4,000 kilometers of magnetic tape without showing significant wear. They were designed to survive some of the harshest conditions ever encountered by a machine. They succeeded beyond expectations. The Voyager tape recorders operated for decades without data loss or major mechanical failures before eventually being shut down to conserve power. Not bad for technology that predates the World Wide Web by more than a decade. Durability was always a primary concern during the mission's planning stages. there were many unknowns. Before reaching Jupiter, both spacecraft would have to cross the asteroid belt, a region once believed to be so densely populated with debris that it could destroy any spacecraft attempting to pass through it. Fortunately, Pioneer 10 and Pioneer 11 had already demonstrated that such a crossing was possible, giving Voyager's team the confidence to proceed. Even so, failure would have ended the mission before it ever reached its first destination. Both spacecraft crossed the asteroid belt without incident, helping confirm what we now know. The belt is largely empty space, yet even after these successes, and despite performing far beyond their designers' expectations, another challenge remained. As the spacecraft ventured farther from the Sun and into the frigid depths of interstellar space, engineers faced a critical question: how would the probes survive such extreme cold? To address this, NASA equipped Voyager with multiple heaters designed to keep essential systems operating under some of the most hostile conditions ever encountered by a human-made object. Nonetheless, as the probe's power reserves gradually declined, NASA was forced to make difficult decisions. To conserve energy, engineers began shutting down non-essential systems, including several onboard heaters. When the heater for the cosmic ray detector was turned off a few years ago, the instrument's temperature dropped by an astonishing 70 degrees Celsius. Needless to say, sending a repair crew 23 billion kilometers into space was never an option. Most experts expected the instrument to fail under such extreme conditions. Instead, it continued operating flawlessly. The fact that both Voyager spacecraft have remained functional for more than 4 decades is a remarkable testament to their resilience and the extraordinary engineering behind them. But with all this technology keeping them alive, what exactly did they discover? To answer that, we need to return to the beginning and follow the trail they carved across the solar system. On August 20th, 1977, NASA launched Voyager 2 from Cape Canaveral, Florida. Its companion, Voyager 1, followed just over 2 weeks later on September 5th. Although both spacecraft were destined for Jupiter, Voyager 1 was placed on a shorter and faster trajectory. As a result, despite launching second, it overtook Voyager 2 on December 15, 1977, and became the first of the pair to leave the asteroid belt. Together, this legendary duo would capture some of the most revolutionary images ever taken in planetary exploration. But rather than simply telling you about them, let's experience the journey ourselves. Just 13 days after launch, Voyager 1 transmitted its first image back to Earth, the first of tens of thousands it would send over the next 5 years. Taken from a distance of 11.6 million kilometers, it serves as a fitting place to begin our story. The photograph may remind you of the famous Earthrise image captured by Apollo astronauts from lunar orbit only 8 years earlier. In the distance, we can see our blue world accompanied by its faithful moon. There's something hauntingly beautiful about this photograph. Knowing how far Voyager would eventually travel and how much it would witness afterward gives the image an almost nostalgic quality. But our journey has only just begun. It would take nearly 2 years before Voyager 1 finally approached its first destination, Jupiter. Considering the giant planet lies roughly 714 million kilometers from Earth, that's an impressive feat. Voyager 1 arrived on March 5, 1979. Traveling at approximately 17 kilometers per second, about 2 kilometers per second faster than Voyager 2, it reached Jupiter 4 months earlier than its sister probe, which arrived on July 9, 1979. The difference came down to trajectory. Voyager 1's path allowed it to gain additional velocity relative to the Sun, shortening its travel time significantly. Now Voyager 1 was not the first spacecraft to encounter Jupiter. That distinction belongs to Pioneer 10, which flew past the giant planet in 1973. While Pioneer delivered valuable scientific data, it never truly captured the public's imagination. Voyager changed that completely. For the first time, humanity saw Jupiter in breathtaking detail. Even today, these images can feel almost unreal, more like paintings or digital artwork than actual photographs taken by a spacecraft hundreds of millions of kilometers from Earth. Look closely, and you'll notice two of Jupiter's most famous moons. On the left is Io, while Europa appears to the right as the pale, beige-colored object. We'll return to both of them shortly. Fortunately, Voyager 1 also documented its approach to Jupiter. The spacecraft captured images every 10 hours, the length of a Jovian day, ensuring that the same side of the planet appeared in each frame. Scientists later combined 66 of these images into a stunning time-lapse sequence, covering Voyager's approach between January 6th and February 3rd, 1979. During that period, the spacecraft traveled approximately 27 million kilometers. It's difficult to decide whether the result is awe-inspiring or slightly unsettling. Either way, it offers an incredible opportunity to take a closer look at what Jupiter was hiding. One of the first things that astonished scientists was the planet's atmosphere. Researchers expected to observe powerful east-west jet streams flowing through Jupiter's various atmospheric bands. What they didn't anticipate was the extraordinary level of turbulence, swirling vortices, rising plumes, and chaotic motion visible throughout the cloud layers. The atmosphere appeared far more dynamic and energetic than anyone had imagined. Scientists had already suspected that Jupiter's most famous feature, the Great Red Spot, was a massive storm rotating counterclockwise. Voyager not only confirmed this theory, but also revealed countless similar storms scattered throughout the atmosphere. The bright white storm located beneath the Great Red Spot is just one example. As it turned out, Jupiter's atmosphere is filled with these gigantic rotating systems, something scientists had barely suspected before Voyager's arrival. When people think of planetary rings, Saturn usually comes to mind. However, data from earlier missions had led some researchers to suspect that Jupiter might possess rings of its own. Voyager confirmed those suspicions. Not only did it verify the existence of Jupiter's ring system, but it also became the first mission to photograph it directly. This image, captured as Voyager departed Jupiter, highlights the rings beautifully. The faint glowing orange line extending outward from the planet is Jupiter's ring system, revealed for the first time in history. Before we leave Jupiter behind, let's return to its remarkable moons, Io and Europa. Perhaps the most surprising discovery of the entire Voyager mission came from Io. Before Voyager arrived, scientists assumed Io would resemble our own moon, covered with countless impact craters accumulated over billions of years. Instead, they found something completely unexpected. Although circular features appeared across the surface, they were not impact craters. The dark regions visible in the images revealed active volcanic hotspots and vast lava lakes. Some lava flows appeared to be less than 1 million years old, extremely young by geological standards and utterly shocking to researchers. Today, Io is recognized as the most volcanically active body in the entire solar system. Even more astonishing, Voyager managed to witness volcanic eruptions in progress. Imagine expecting to find a barren, cratered world, only to discover a moon violently reshaping itself in real time. The enormous blue plumes visible in these images blasted gas and material more than 100 kilometers above the surface. Io's volcanoes erupt continuously, sometimes every few hours, providing Voyager with some of the most spectacular images of the mission. The next moon outward, Europa, could hardly be more different. Covered in ice, Europa appeared as a smooth, frozen world, crisscrossed by mysterious dark streaks and fractures. Voyager was the first spacecraft to reveal these strange markings, which scientists believed were enormous cracks in the moon's icy crust. Even more importantly, the mission provided the first clues that a vast liquid ocean might exist beneath that frozen shell. Today, Europa is considered one of the most promising places in the solar system in the search for extraterrestrial life. At present, astronomers have identified 95 moons orbiting Jupiter. Before Voyager arrived in 1979, only 13 were known. The mission discovered 3 additional moons, Metis, Adrastea, and Thebe, raising the total to 16 by the early 1980s. Although detailed images of these small satellites would come later, their discovery was yet another major scientific achievement. With Jupiter behind them, the Voyagers set their sights on the next destination of their grand tour, Saturn. After 21 months of travel, Voyager 1 reached the ringed planet in November 1980, with Voyager 2 arriving 9 months later in August 1981. And when it comes to Saturn, there's only one place to begin: the rings. So, Voyager was sent to follow up. It found that Titan had a thick, nitrogen-rich atmosphere, the first and only such atmosphere encountered beyond our home planet. Enceladus also turned out to be exceptionally peculiar. Take a look at this photo. Enceladus is visible in the distance, with Saturn in the foreground. Now, I know it's tricky to see, but that moon is erupting. Enceladus spews out 300 kilos of water vapor up to 10,000 kilometers above its surface, 20 times its own diameter. As it orbits Saturn, the frequent plumes of water vapor leave a donut-shaped cloud that feeds one of Saturn's icy rings. This was suggested by Voyager data, but it wasn't until the Cassini mission that we could confirm it. Further geological data and imaging show that Enceladus's terrain is an unexpected mixture of old and new. The left side, which appears smooth, is the newer terrain, while the right side, densely packed with impact craters, is the older one. This suggests Enceladus is a far more geologically active moon than previously thought. Before we make our way to the peculiar world of Uranus, we have to say goodbye to Voyager 1. After its flyby of Titan and Saturn's rings, its path was bent upward out of the ecliptic plane, sending the probe straight toward interstellar space. Of course, it would be another 32 years before it actually reached it. Not to worry, though. Voyager 2 used a gravitational slingshot around Saturn to propel it onward to Uranus and Neptune. These would be the first and only flybys of those planets in human history. 5 years after arriving at Saturn, Voyager 2 approached Uranus in January 1986. At its closest, the probe came within 81,500 kilometers of Uranus's cloud tops. Voyager 2 revealed a notable absence of visible cloud features in Uranus's atmosphere. Unlike Jupiter and Saturn, Uranus displayed a serene, featureless cloud deck, challenging scientists' preconceptions about the atmospheric dynamics of gas giants. The false color image on the right highlights subtle differences in the atmosphere of the polar regions, which are tilted on a 98-degree axis. But it was another tilt that stunned Voyager scientists. It was previously unknown whether Uranus had a magnetic field, but Voyager data revealed not only that it does, it is also tilted at an astonishing 59 degrees. That means its magnetic and rotational poles are nowhere near aligned. Until then, it was assumed these poles were always closely aligned, as they are here on Earth, where the offset is only 12 degrees. This stark deviation defied conventional planetary magnetic field models and forced scientists to rethink their assumptions. One side effect of this misalignment is that as the planet spins, its magnetosphere, the region carved out by its magnetic field, wobbles like a poorly thrown football. Scientists still don't fully understand how to model it. Voyager 2's observations confirmed more details about Uranus's known rings and discovered 2 additional ones. It was the first mission to capture images of these dark rings, including the outermost ring visible in this photo. The rings are composed of fine dust particles. Voyager 2 also discovered 2 shepherd moons orbiting one of the newly found rings, similar to its findings near Saturn's F ring. They can be seen here from 4 million kilometers away, in a photo taken on 21st January 1986. The mission significantly increased the known count of Uranian moons. Prior to Voyager 2, only 5 moons orbiting Uranus were known. Voyager 2 delivered the first-ever images of these moons, and also discovered 11 more, bringing the total to 16. Today, the number of known moons stands at 27. Back to Uranus's 5 original moons. They all appear to be ice rock conglomerates, similar to the moons of Saturn. Oberon and Umbriel, pictured here on 24 January 1986, are riddled with impact craters and show little signs of geologic activity, judging by their old, dark surfaces. Titania, the 4th furthest from Uranus, is marked by vast fault systems and canyons, indicating some degree of geologic and likely tectonic activity in its past. Ariel has the brightest and possibly youngest surface of all the Uranian moons. A photo taken from just 129,000 kilometers suggests Ariel underwent geologic activity that produced numerous fault valleys and extensive flows of icy material at some point in its history. Miranda, the closest of the 5 to the planet, provided the most surprising findings. Voyager flew by Miranda on 4 January 1986 at a distance of just 30,000 kilometers. This small moon turned out to be a captivating geological puzzle shaped by a volatile history. Voyager 2 identified signs of internal melting and sporadic upwelling of icy material, manifesting in extensive canyon-like faults, plunging to depths of up to 20 km. The lunar surface is further marked by oval, racetrack-shaped features etched like cosmic scratches, as well as terraced regions where old and young, bright and dark, and heavily and lightly cratered terrains coexist. The chevron-like formations suggest Miranda's original surface was torn apart and the fragments forcibly reassembled. 3 weeks later, on 25 January, Voyager 2 departed Uranus and captured this wonderful farewell image from 1 million kilometers as it set off toward its final planetary target, Neptune. After 3 years of travel at 54,000 km/h, Neptune finally came into view. Voyager 2 approached the outermost planet in our solar system on 25 August 1989, just over 12 years after launching from Earth. It produced the first close-up images ever received of the giant blue planet, passing only 5,000 kilometers above its north pole, the closest approach of any flyby. Hydrogen was found to be the most abundant element in Neptune's atmosphere, though its high concentration of methane gives the planet its characteristic blue color. Voyager 2 measured extraordinary wind speeds in Neptune's atmosphere, with equatorial winds reaching nearly 100 km/h. These remarkable speeds were yet another surprise, underscoring just how dynamic and ferocious Neptune's weather systems are. Scientists also discovered a massive storm on Neptune, aptly named the Great Dark Spot. This turbulent system appeared to rotate counterclockwise, much like Jupiter's Great Red Spot, and produced winds of up to 2,400 km/h, the strongest ever recorded in the solar system. NASA analyst Ken Bollinger commented on the findings in 1989. "Every day what you see is brand new. Nobody's ever seen it. It's just an incredible feeling. There are changes going on constantly on Neptune, and they happen very, very fast." Voyager 2 also imaged Neptune's rings for the first time. Up until 1986, scientists had suspected the planet might have rings, but couldn't be certain. Intriguingly, the spacecraft identified several partial ring structures, known as ring arcs, within Neptune's ring system. These arcs raised questions about the mechanisms responsible for their formation and stability, as they consist mainly of incomplete, dusty rings. A trip to Neptune wouldn't be complete without a visit to its largest moon, Triton, the coldest known body in the solar system. Triton turned out to have a fractured surface complete with erupting geysers and a pinkish nitrogen ice cap over its southern pole. Scientists also identified dark plumes that may indicate the presence of ice volcanoes. Voyager 2 additionally discovered 6 new moons orbiting Neptune. As Voyager 2 turned around for one last look at Neptune and Triton, it had officially completed its grand tour. Neptune's gravity bent its path downward out of the ecliptic plane, and from there it continued its voyage into interstellar space, just as Voyager 1 had done 9 years before. Speaking of Voyager 1, 1 year after Voyager 2 wrapped up at Neptune, it was already roughly 6 billion kilometers from Earth. To conserve power for the long journey ahead, scientists plan to shut off its cameras permanently. However, on Carl Sagan's recommendation, the team decided to turn the camera around for one final image, a look back at home and at how far we had come. And so, on 14th of February 1990, Voyager 1 took the most remote selfie in history from 6 billion kilometers away. The result was the iconic pale blue dot photograph. In the immortal words of Carl Sagan himself, "Look again at that dot. That's here. That's home. That's us. On it. Everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was, lived out their lives." The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species, all lived out their lives on a mote of dust suspended in a sunbeam. There is perhaps no better demonstration of the folly of human conceit than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. This sentiment carries as much power today as it did 33 years ago. But what came next? What did the Voyager probes see and do in interstellar space? In 1981, Voyager 1 escaped the ecliptic, the plane of Earth's orbit around the Sun, heading 35 degrees to the north. Voyager 2 later passed beneath it, heading 48 degrees to the south. Even so, this was barely the beginning of their journeys. To reach interstellar space, the probes would have to traverse the termination shock, a region where hypersonic solar winds meet fierce resistance from the interstellar wind. Beyond the termination shock, the Voyagers would encounter the heliosheath, where slowing solar winds pile up, growing denser and hotter, before finally reaching the heliopause, the boundary between the heliosphere and interstellar space. But despite what you might assume, crossing into the interstellar medium does not mark the end of our solar system. It will be another 300 years before Voyager 1 reaches the Oort cloud, the vast region of billions of icy planetesimals that surrounds our solar system like a bubble, and another 30,000 years before it exits the cloud and leaves our solar system for good. As the Voyagers traveled through the heliosheath, they made a remarkable discovery. Because the Sun's magnetic field spins in opposite directions at its north and south poles, the interaction creates a ripple where they meet, known as the heliospheric current sheet, somewhat like the rings formed when a stone is dropped in water. However, when this sheet reaches the termination shock, it compresses, as though those ripples were hitting the edge of a pool. The Voyager probes discovered that beyond the termination shock, these stacked-up ripples form magnetic bubbles, revealing that the boundary of the heliosheath is far from the smooth, clearly defined region scientists had envisioned. Instead, it is a turbulent, magnetically bubbly environment, a finding that prompted a complete revision of our model of the heliosheath. On 25 July 2012, Voyager 1 became the first human-made object to leave the Sun's heliosphere and enter interstellar space, traveling at an extraordinary speed of 540 million kilometers per year, or 3.6 astronomical units, where 1 astronomical unit equals the distance between the Earth and the Sun. The crossing occurred approximately 120 astronomical units from the Sun, which was itself a revelation. as the precise location of the heliopause had never been known. Early models had placed it as close as Jupiter. Others had put it far further out. The heliopause, to be clear, is the boundary where the Sun's solar wind is halted by its collision with the interstellar medium, much like two powerful bodies of water crashing into each other. Solar wind is the steady stream of charged particles, electrons, protons, and alpha particles, that flow outward from the Sun's outer layer. The interstellar medium, by contrast, consists of charged particles, gases, and cosmic dust left over from the Big Bang and ancient supernovae. When these two streams collide, they change course and form a region of equilibrium, the heliopause boundary. At first, NASA was not entirely certain that Voyager 1 had truly crossed the heliopause. As models had predicted, the probe's plasma wave detector registered a massive increase in plasma density, 80 times what it had measured in the outer Helios sheath, along with a spike in galactic cosmic rays. But one expected change never came, leaving scientists baffled. After crossing the heliopause, Voyager 1 detected no change in the ambient magnetic field. This was deeply surprising, because theoretical models had assumed the magnetic orientation would shift in a region dominated by the fields of other stars. NASA was so uncertain that they waited nearly a year before officially announcing that Voyager 1 had entered interstellar space. On 5 November 2018, Voyager 2, traveling at a slightly slower speed of 490 million kilometers, or 3.3 AU per year, became the second human-made object to enter interstellar space. Its crossing also occurred at 120 AU from the Sun, and like Voyager 1 6 years earlier, it too detected no change in the ambient magnetic field. But something else caught scientists off guard. The Sun undergoes 11-year solar cycles, during which its activity rises and falls. Voyager 2's crossing occurred during a period of peak solar wind activity, and models predicted the heliosphere would have been expanding at the time. Yet Voyager 2 crossed the heliopause at precisely the same distance as Voyager 1, meaning our models were wrong again. Like the magnetometer findings, this demonstrated the invaluable role of field data in testing theoretical models. Scientists now suspect the boundary between the heliosphere and interstellar medium is far more distorted and turbulent than previously thought. One leading hypothesis is that our Sun formed billions of years ago from a hot, heavily ionized region created by one or more supernova explosions, and that magnetic turbulence from that event persists near the heliopause to this day. If so, the probes may eventually encounter a different magnetic orientation further out, though their instruments will likely have gone dark long before then. Indeed, the probes are already beginning to fail. In early May 2022, Voyager 1's signal turned strange. Imagine you are a NASA scientist. You sit down at your computer and begin reviewing Voyager 1's telemetry data. The routine status updates the spacecraft sends back to let engineers know whether its systems are functioning normally. A signal now takes 22 hours to travel from Voyager 1 to Earth, so communication is slow. It is less like sending texts and more like exchanging letters. But today, something is wrong. Instead of precise data describing what Voyager 1's thrusters are doing and what orientation it believes itself to be in, you receive long strings of zeros and 3747s. Complete nonsense. The data suggests the spacecraft is doing things and pointing in directions that it simply cannot be. You check again. A signal from Voyager 1 has definitely arrived, which means its antenna must still be pointing toward Earth, exactly as it always has. If it were pointing elsewhere, no signal would reach you at all. And not only is the signal present, it is at full strength, confirming the antenna has not shifted. Then, your computer pings. The latest science data from Voyager 1 has arrived, and it is entirely normal. Though Voyager 1 has had to power down 5 of its original 11 scientific instruments over the years, and 2 more have stopped working due to general degradation. The remaining 4 continue to take readings on the interstellar medium, magnetic fields, and cosmic rays without issue. None of this data is garbled in any way. You check the other systems. Power levels are running a little low, but that is to be expected. The plutonium oxide fueling its 3 generators has a half-life of 87 years, yet Voyager 1 has been traveling for 45. A decline in efficiency is entirely predictable, and experts believe the probe will not remain operational much beyond 2025. But that doesn't explain what is happening right now. After working through each system, you isolate the problem. It is only one component behaving strangely: the AACS, the Attitude Articulation and Control System. This is one of 3 computers aboard Voyager 1, and its job is to ensure the spacecraft's large 3-meter antenna remains pointed toward Earth at all times. The AACS has stopped sending coherent data. You lean back, puzzled. The situation is not as dire as it might initially seem, but it is deeply troubling. It is a little like a postman who greets you reliably every morning, only to one day start speaking in a language you cannot understand. The packages still arrive. The address is still correct. His words, however, make no sense. Stranger still, Voyager 1 does not appear to think anything is wrong. The spacecraft is equipped with emergency safe mode settings that activate automatically if it detects a malfunction, essentially powering down non-essential systems while scientists work out a fix. These have not been triggered. As far as Voyager 1 is concerned, all systems are operating normally. That was the puzzle NASA engineers faced in mid-2022. A single fault like this might not seem catastrophic in isolation, but it hints at something deeper. And if a wider problem is developing, it could spell the end of the entire mission. Voyager 1 is now 23.8 billion kilometers away. Any solution must be reasoned through by deduction, with each question and answer requiring a 22-hour round trip between Earth and a spacecraft that may not even understand something is wrong. By ruling out the systems that are functioning normally, you can eliminate some of the more far-fetched explanations. No, this is probably not the work of aliens attempting to interfere. While NASA scientists did leave open the possibility that the Voyager probes might one day be discovered by extraterrestrial life, as evidenced by the golden records installed aboard each probe, filled with messages about humanity for any alien that might stumble across them. That was always more of a symbolic gesture than a genuine expectation. Besides, garbling a spacecraft's attitude data seems like a rather odd way for an alien civilization to make first contact. And no, the laws of physics have not broken down. Voyager 1 has not passed through a wormhole that is distorting its sense of orientation, while somehow still managing to relay signals back to Earth. Given that all the scientific data continues to read normally, the most likely explanation is that the fault lies with the AACS itself. For 4 months, scientists and engineers carefully prodded and examined Voyager 1's. Voyager 1, testing theory after theory and searching for a solution that would fix the problem without causing any further damage in the process. One option was to switch to a backup system. This would not be the first time a replacement computer had been brought online aboard Voyager 1. The probe was built with redundancies, and this was not even the first AACS unit in use. A previous one had become defective some time ago. Another option was simply to leave things as they were. After all, the science data was still coming through. Would it really matter if Voyager 1 continued sending garbled status messages? Perhaps this could just become the new normal. The problem with that approach, however, was that it risked masking a deeper underlying issue. Can you figure out what was actually going wrong? If so, perhaps NASA should consider hiring you. It turned out that in the intense radiation-filled environment of interstellar space, something had caused Voyager 1 to begin routing its data through the older, faulty AACS computer rather than the correct one. The faults in that unit were corrupting the output, producing the meaningless strings of numbers. In the end, the fix was straightforward. NASA simply needed to instruct Voyager 1 to start using the right computer again. Once it did, the problem was resolved. Though I use the words straightforward and resolved loosely, it still took several months for Voyager 1 to return to normal operation. And then, in November 2023, yet another onboard computer, the Flight Data Subsystem, developed a similar problem and became unable to transmit usable science or engineering data back to Earth. It was not fully resolved until June 2024. Voyager 1 is an aging spacecraft, and as it continues its journey through interstellar space, it may face more and more faults. In July 2023, a routine set of commands sent to Voyager 2 caused the probe to shift its antenna orientation by just 2 degrees away from Earth. That seemingly minor deviation was enough, across the vast distances involved, for NASA to lose all contact with the spacecraft entirely. It was only through broadcasting an interstellar shout from the Deep Space Network facility in Canberra, Australia, that engineers were able to send a signal instructing Voyager 2 to reorient its antenna back toward Earth. The 37-hour wait for the signal to arrive, and for the probe to confirm it had followed, the command must have been agonizing for the NASA team. The probe could so easily have been lost forever. One way or another, it is inevitable that the Voyager probes will eventually fall silent. Whether through error, malfunction, or simply running out of power, the end is unavoidable. And the curtain will one day fall on this extraordinary mission. But even then, the twin probes will only just be beginning their cosmic journeys. In 40,000 years, Voyager 1 is expected to drift toward a star in the constellation Camelopardalis, while Voyager 2 will pass within 1.7 light-years of the star Ross 248. In 296,000 years, it will pass 4.3 light-years from Sirius. These small, intrepid probes will likely outlast the Earth itself, continuing their solitary wanderings across the Milky Way for aeons to come. And if, by some extraordinary chance, they are one day encountered by intelligent life in some distant corner of our galaxy, they will stand as a testament to human ingenuity and resilience. Aboard each probe is a message to the stars, the Golden Record. These golden audiovisual discs carry photographs of Earth and its many life forms, the sounds of whales and of newborn babies crying, music by Mozart and Chuck Berry, and greetings in 55 languages spoken by people from dozens of cultures around the world. They offer any distant stranger who might find them a glimpse of who we are and what life on Earth is like. As for us, we must say farewell to these old and familiar companions and carry on with our own lives here on Earth. Hopefully, the Voyager mission will not be our last brush with the stars, but only the beginning.